Okay, welcome to Math 219, Section 1, I guess this is. Glad to have you in the class. First thing I need to observe, as is hopefully clear, we are recording. I've been recording my lectures for many years, since long before COVID, and it gives students a reference to look at afterwards. You know, if you miss something in class, it's nice to be able to just kind of rewind the tape, right after class is over and what was that again? And sometimes it makes a lot more sense second time through. Okay, all right, so we are recording. You've been officially informed. Now y'all have already watched, presumably, hopefully, the recording that I made a couple of days ago about sort of logistics and, kind of general first day comments, how to do well in this class, what the expectations are, etc. So I'm not going to repeat all of that. I just want to hit a couple of quick highlights. So the Sakai sites, do make sure to read all of the text on the Sakai sites. It's all important. It's all relevant to how the class proceeds and, how grades work and what the policies are for this, that, and the other thing. So make sure that you read all that stuff. So that's the first reminder. Next, I want to comment real quick about course grades. Again, I talked about this in great detail on the recording, but I just want to remind y'all, if you're unclear about any of that, about how grades work in this class, come talk to me. I'll be very happy to explain it. It's ultimately a pretty simple formula. I mean, there's a communication confusion, but the formula itself is not itself confusing, but it's just a matter of, communicating it and making sure it's clear what simple formula it is. Anyway, if you're at all unclear how that works, come talk to me. Happy to explain it. Okay. And then lastly, and again, I don't want to get off onto my soapbox. This is one of my soapbox topics, but make sure to come at this course the right way. Right? This is not a course where you just have to know the formulas and you're good. It's just not. This is a class about ideas. You need to understand ideas and be able to make connections in your mind between ideas in order to be able to solve problems. Very often that's how it works in the real world, is that, you have some problem to solve and you need to understand, this aspect of it reminds me of that idea that I learned, and this other aspect reminds me of some other idea that I learned, and you got to be able to make connections between them. So that's what the course is about. Make sure that you, in your studying and in your doing the homework exercises and in your, the way that you use your time in class, what you focus on thinking about in class, think about and focus on the ideas. I mean, now you also do have to also know the formulas. Yeah, right. And you do have to be able to execute the algorithms, and you do have to know certain facts, terminologies, etc. Yeah, of course. But it is very important also that fundamentally what we're really interested in, those are all in service of helping us understand ideas. Okay. All right. I don't think I got too far into my soapbox there. The rest of this stuff, again, it's on that recording. Make sure that you watch that recording. And let me pause for questions before I go on to get into some math. Anybody? Everybody's good? Anybody have any trouble watching the recording? Apologize for the warp wire snafu. I don't know. I've had trouble with warp wire in the past, but YouTube always works. All right. Okay, moving along. Okay, so before we get into the book material, I want to start with I want to make my case for why you're here, why you're taking this class. So, why are you taking this class in the first place? And I understand that for many of you, you're taking the class because your major requires it. And that's a nice, simple answer, right? But let me then go to the natural next question. Why does your major require it? Right? It's multivariable calculus is important. Now, I'm going to try to make the pitch as to why. And I'm going to start with what I think you probably already buy into, I hope, and that is that single variable calculus is important. Single variable calculus is ridiculously important. So if you think about it, derivatives, one of the main objects of study in single variable calculus, anytime you're looking at a situation where something's changing, derivatives are what describe how it's changing, right? Any quantifiable object, right? So the world is full of change, right? So of course derivatives are important. That's a pretty easy pitch to make, I think. So integrals. Now a lot of people misunderstand what integrals are. This is another one of my little soapbox topics that I'm going to try to stay off of, but a lot of people mistakenly think that the purpose of integrals is to compute area under a curve. At most, that's a kind of a metaphor. It's a geometrically convenient example, perhaps. It's really not the purpose of integrals. Well, why is it important to understand integrals? It's not because we just have this unbelievably huge need to compute areas under curves. It's just not. That's not what it is, right? What we need very often is to compute what I like to call accumulating quantities. Quantities which, you can chop it up into little pieces, and if you just compute all the individual pieces and then add up the quantity in question over all those pieces, then you get the total that you're interested in. So the world is full of accumulating quantities, right? And yeah, area under a curve is also an accumulating quantity. Really not the most interesting one, not even on the top 10 list. Again, the world being full of accumulating quantities, that's why integrals are important. Right. So again, I think this is stuff that y'all have all already understood, but I wanted to start with that and then point out that the world we live in is multivariable. And we live in what I'll loosely call a three-dimensional world, not a one-dimensional world. And so single variable calculus is kind of not really quite the right natural fit, and certainly in a lot of instances. So here's a couple of questions that we can talk about that are a little bit more real world, perhaps, a little bit more general than the single variable special cases that maybe that you saw in your single variable classes. So here's a really natural, simple question. Let's suppose temperature varies throughout space, throughout the room. Let's say we're in this room here, and I'll bet it's colder over there by the windows and it's warmer wherever the heat's coming in, to the extent that it's coming in, and various different, it's probably a little bit warmer closer to the human bodies, right, and a little bit colder near the wall. So the temperature varies. Okay, well, if you are at this location, right, and you start to move at some angle, you're not moving straight up or straight left or exactly in a rectangular direction. You're moving it kind of that way. How fast is the temperature changing? Right, reasonable question to want to ask. And this is not a single variable calculus problem. Right? In single variable calculus, we don't have functions of three variables. And then when we take their derivatives, how do we account for, how does the direction that we're going factor into taking a derivative? Right? This is not single variable calculus. So, this is what calculus very often looks like in the real world. Right? Our three-dimensional world. And so multivariable calculus is how we adapt the ideas of single variable calculus to a kind of a real world context. Here's another example. And I think y'all probably all recall in single variable calculus classes the classic example of you've got a one-dimensional rod made of some kind of a metal. It's an alloy, and the density is greater over here and it's less over here. And how do you compute the total mass? Right? If you know mass per unit length all the way along the whole thing, how do you compute that total mass? And the idea is you chop it up into little pieces, right? You make a Riemann sum, aka an integral, and then you basically you do an integral where you're adding up those little pieces. Fine. Okay. There are even, in fact, a reasonable number of cases where we have kind of sort of one-dimensional rods. They're not exactly one-dimensional, but we think of them as one-dimensional in the sense that they're long, but they're pretty thin, and we don't think about their mass per unit volume within the rod. We think about rod and chain and rope and stuff like that as per unit length, right? So it's effectively one-dimensional, but it's kind of a peculiarity. really. And most of the time when we're talking about mass, we talk about mass per unit volume. So suppose we have a great big lump where the density varies, just like in our rod example, but this time the density is not just a function of one variable. Here, the density depends on all three variables. And so, for example, maybe the density, this density here, maybe it's, kind of, that's sort of the minimum, but it's more dense over here, this side of the lump. And maybe also more dense down here on this part of the lump. All right, compute the mass of that thing. Well, it's not a single variable calculus problem. I can't multiply mass per unit length times length because it's not about length. And the mass isn't per unit length, it's per unit volume. What do we do here? Right? So this is analogous to a single variable calculus problem that we've seen and that we know how to solve, but it's pretty different. Right? There's a worse problem here that kind of doesn't even come up in single variable calculus, and that is, how do we account for the fact that there's a shape to this? This isn't a rectangular deal, right? I can't just say integrate from A to B. What, from here to here maybe? Right? But what about all the shape and the fact that there's a shape to this? It's kind of narrower here and wider there. That's got to matter. How does that factor into the calculation? So this is all stuff that we're going to cover in this class. This is multivariable calculus. These are just some kind of starter easy examples. I want to show you now some more sort of like field dependent examples. So I'm going to show you an economics example. This is not a real example. The economics of this is not the point here. But very often, the way economics works is you have certain quantities, price, quantity produced, that doesn't highlight well, does it? Okay. Interest rate, capital, labor, these are standard quantities of interest in econ. And what we do in economics is we create something called a model, right? So we write down an equation, or possibly several equations, that describe a relationship between these variables. Importantly, notice, this is not L is the following function of the other variables, or, P is the following function of the other variables. I might not know such a function. I don't know. And notice here in particular, P, you can't solve for P. Right? So very often that's how it works, and you have a model that's an equation in which you can't really solve for the variables you're interested in. You can involve them in an equation, you can't solve for them. So, okay, that being the case, if this is my model, this is how I'm going to try to understand some economic scenario, and suppose that these variables here, maybe I can control them, or maybe I can observe how they change, or maybe I'm interested in understanding a scenario, possible future scenario in which these variables are changing in certain ways. Reasonable question to want to ask, what about the other variable? How does it change as a result? I mean, if this equation has to stay true, and if I just start fiddling with some of the variables, the equation's not going to work. A P is going to have to change in order to keep the equation working. In other words, for our model to be obeyed. So how do you do this? How do you, if I understand the rates of change of L, K, Q, and I, how do I understand then the resulting change in P? Right, so now this is it's a hard problem. This is another question that we're going to study in this course. This is called implicit differentiation. You've probably seen implicit differentiation in Calc 1 classes, I guess it would be. We're going to see a multivariable version of that. So, so this isn't, notice this is not a physicsy kind of example. A lot of people must make the mistake of thinking that, math is a tool that serves physics and engineering, maybe a little chemistry, right? And, yes, but it's certainly not limited to that. Math serves a lot of different fields. Economics is one of the really big ones, in fact. Being able to solve economics problems is a huge application for math. Okay. There's another point of interest on this example that I like to make, and that is a lot of people like to, in doing multivariable calculus or linear algebra or something like that, say, okay, well, look, we live in a three-dimensional world, so we're not going to go over 3 dimensions. We have to. Can we even really talk about more than 3 dimensions? What is the 4th dimension? And then the conversation turns kind of sci-fi-esque, right? And you're like, is this a Doctor Strange movie? Is there time travel going on here? What's going on with wormholes? It sounds creepy and weird. But notice, in this pretty innocent little example about economics, this isn't cosmology. Right? This is just economics. We're just trying to keep track of the money, right? Notice that we have 5 variables that we're keeping track of, as they are functions of one time variable. So altogether, we have 6 variables here. We're doing 6-dimensional math here. Right? So again, common mistake that students and sometimes instructors make, in my opinion, on teaching multivariable calculus is to say, well, 2 and 3 dimensions only. That's it. No, we're not going to go above 3 dimensions. It gets weird. And it really doesn't. Right? There are some aspects of it that are weird and hard, and you can't draw pictures. Don't try to draw a picture in 6 dimensions. That's not going to work. Right? But it is not at all abstract or incomprehensible or irrelevant. This is not ivory tower, abstract mathematicians doing math for math's own sake. This is a very practical, relatable econ problem, right? And it takes 6 dimensions. So anyway, I like to point that out too. Okay, pausing. I said a lot there. Pausing for questions. All right, here's a scary-looking example. So these are called Maxwell's equations. So these are special cases. These are what we might call the standard special cases of Maxwell's equations. If you've had an E&M class, you've probably seen these before. If you have not had an E&M class, don't worry about it. Seeing this first, well, not what I'm about to show you right this second, but seeing what I'm going to show you about multivariable calculus and how they relate to Maxwell's equations will give you a big advantage when you do take an E&M class, if you take an E&M class. So anyway, but just as an example, again, under the heading of why do we need to understand multivariable calculus? Well, if you're studying physics or engineering, you're going to need to understand E&M, right? Electricity and magnetism. And electricity and magnetism, a large part of understanding electricity and magnetism is understanding Maxwell's equations. And if you look and see what we have in here, well, we have, that's a calculus-looking thing, but never seen 3 of them in a row before. Well, this is an object of multivariable calculus. And what is dv as opposed to dx or dy? Well, we'll talk about that when we get to it. Here's a weird one. This appears to be a differential at the end of an integral, except it's a vector. What's going on there? Right? What does that even mean? Right? So there's a lot of things that we need to understand in here. We need to understand what the individual mathematical objects are here. But there's more to understand, and that is, what is this equation saying? Why is it true? And what does this help me understand about electric fields? Right? And again, these are the big ideas, right? That these are among this is in the category of the big ideas. What this class is really about is interesting, useful truths of math, where they come from, why they're true, and what they help us understand about other things. Right? So that's going to be an object of interest. You'll notice we have 8 equations here that I have in the box. You may have heard of Maxwell's equations as being full of, 4 equations. Why 4? There's clearly 8. Well, very often people will describe these 2 seemingly separate equations as being, pretty much the same equation. How does that work? They don't look the same. They look dramatically different, don't they? So there is a really good reason why physicists, mathematicians consider these to be two different versions of what's morally the same statement. How does that work? Right? So that's another thing that we're going to be talking about in this class is when we get to the E&M stuff, is why is it, in what way is it that these two equations are actually related to each other? Okay, so a lot to understand there. A lot of multivariable calculus that's going to be very relevant to physics and engineering majors. Okay. So here's another one. Now we're not going to be studying this one in this class. This is called Schrodinger's equation. So it's not that we couldn't, but we just don't really quite have time to get into it. But this is a really relevant thing to understand for chemists and physics majors. So in particular, molecular bonds, right? Big deal in chemistry. Very big deal. Where do molecular bonds come from? Well, they come from the behavior of electrons, as it turns out. Okay. How do electrons behave? What controls how electrons behave? And, well, the answer is Schrodinger's equation. So if you want to really understand how chemistry works, why chemistry works, you need to understand Schrodinger's equation. And what is Schrodinger's equation? Well, this thing right here, it's called the Laplacian operator, and it is, roughly speaking, it's an object of multivariable calculus. So if you if you're a chemistry major and you want to have some sense and understanding of why molecular bonds work, at some point you're going to need to understand multivariable calculus so that you can get started on understanding this equation. And there's much, much more to it. Schrodinger's equation is a little bit of a bear to deal with. I have bad memories of being an undergrad physics second major and having to solve Schrodinger's equation in various circumstances. And it's a lot of work. So again, not part of this class, but to the question of why do we need to understand multivariable calculus? Well, I think that's a pretty persuasive point. Okay. All right. Alrighty. So now these are just a few of the applications that are out there. I picked what I thought would be, the most easy examples, the most powerful examples, the most interesting examples, right? But the world is just full of such applications. And in fact, this is the way I like to say it, multivariable calculus is the calculus of the real world. The real world's three-dimensional, not one-dimensional. Right? And so if you're going to do calculus in the real world, you're going to be doing calculus in, let's say, 3 dimensions, possibly more. So real world, you need multivariable. Okay. All right, how are we doing? Questions? Feel free. Is everybody sold on the idea that multivariable calculus is important? Okay. All right. Okay, moving along then. So now we're going to get into the book material, and I want to remind you that again, I talked about this a lot in the pre-recording that you've already watched, and I'm going to try to stay off of my soapbox. But the way that you're going to approach this course is not just come to class and try to understand what was said in class and that's it. So the book is a separate resource. The book is more thorough than what I can possibly do in class. We just don't have time. It wouldn't be at all feasible. And it also, it just wouldn't be an effective use of time either. So what I'm going to be doing, one of my challenges as an instructor in this course is to make the tough choices on what am I going to spend time on and what am I not going to spend time on, and just leave to y'all to study on your own. If you think about it, it's not that weird. They do that in history classes too. You take a history class, you read 500 pages of a book, and class, well, they talk about one aspect of something that you read, but you got to read the whole thing, right? So same thing here. So I'm going to hit what I think are the most important highlights, the things that I think are the most challenging, the things that you will need the most help with, the things that are most important. That's takes some priority as well, and the things that are the most effectively understood with me being able to draw pictures, me being able to talk to you live as opposed to just reading it out of a dead book. Right? So it's a combination of considerations, and the punchline is some topics will be able to be discussed in class and some won't. So a lot of Chapter 1 is stuff you've probably seen before, at least to some extent. Most of it is a relatively easy read, and a lot of Chapter 1 I am going to leave to y'all to read on your own. Not all of it. We're going to spend quite a bit of time on Chapter 1. But there's going to be a bunch of stuff that's in the book that we're not going to have time to talk about and that you have to read. Again, you're still responsible for. Okay. So starting with, weirdly, Section 1.6. Section 1.6 is where the author of the book gets around to talking about some aspects of linear algebra. Y'all presumably are just coming out of a linear algebra class. I hope you still remember a lot of that stuff. You don't need to remember at least for this class, you don't need to remember some of the more, far out stuff like Jordan canonical forms. It's not going to come up in this class at all, right? But some of the basics are going to be used fundamentally in this class, right? So I want to hit certain highlights and certain topics just to make sure that you've seen and understood everything that we're going to use. I'm going to start off with the triangle inequality, not because this is going to be so dramatically important, but because it's possible that you might not have seen it in Math 218. I'm not sure. Maybe they did. Maybe they didn't. So here it is. Triangle inequality says this. Here's a picture of the objects in play there, a couple of vectors and their sum. And I like to think of this as saying that distance is less than or equal to, well, let's see here, the sum of these two distances. And I like to interpret that as saying that between these two blue points, the shortest distance, the distance between those 2 points that's less than the others, is the straight line. And so very, very geometrically believable statement, right? But nevertheless, something we can write down in an equation and is useful sometimes. So does everybody buy it? Everybody happy? Question for my own curiosity. How many of you, show of hands, did see this fact in Math 218? Okay, good. So I'm glad I mentioned it. Good. Okay. By the way, to the question of how do we know this is true, how do you prove this equation, that is a linear algebra problem. And if you want to play around with it, it'd be a healthy exercise. The proof, I'm fairly sure, is in the book if you want to get the reveal. And if you have trouble and if you can't find it in the book, you can come ask me. Okay. But again, it's not part of the course. This would just be a kind of polishing off your linear algebra if you're interested. Okay, matrix multiplication. I am quite sure that you all know how to multiply a matrix times a vector. What I am not 100% sure on is that you know all of the different and, in their own ways, all important different ways of multiplying a matrix times a vector. So the one that's most common is where you take the rows of the matrix and then you dot with the vector, and those dot products give you the elements, the individual coordinates of that product vector. Okay, so that one is computationally convenient. It is occasionally useful mathematically. It's mostly, though, just computationally convenient. If all you're going to do is take matrices of actual known numbers and multiply by vectors of actual known numbers, then it's a great one and I'm a fan. But here's the thing. That's not usually the issue, right? Computers can do that. We don't really need y'all to be cranking that out by hand, right? What you can do and what computers can't do, and I talk about this a little bit on the web pages, on the Sakai site. There's a bunch of discussions there. I'll talk about this a little bit there. What you can do that the computers can't is understand and manipulate ideas, right? And to this point, computers can't really do that, Right. So anyway, here is an idea. I think this is really valuable. This is going to come up in various places in the course, including later today. A different point of view that you can take on matrix vector multiplication is that a matrix vector product is a linear combination. So, notice this starts off very differently from that dot product formula that would say something along the lines of a matrix vector product has coordinates which blah blah blah. Right? I'm not describing the matrix vector product by its coordinates. I'm telling you directly here what the matrix vector product is. So it's a linear combination. Linear combination of what? Well, it's a linear combination apparently of these things, which you'll notice are the columns of the matrix. Right, so there you go. Matrix vector product is a linear combination of the columns of the matrix. Specifically, what kind of a linear combination? What are these coefficients in the linear combination? Well, here they are. The coefficients in the linear combination are the coordinates of the vector that you're multiplying. So it's not hard to confirm that this point of view on matrix multiplication will give you all the same answers as the old dot product, computationally convenient formula. But this one is more, more usefully anyway, about ideas and objects. In particular, notice that this one starts off first thing by telling you fundamentally what the object in question is. We're interested in a matrix vector product. It's a linear combination. As opposed to, what's a matrix vector product? Let me tell you about its coordinates. Right? It doesn't really get right to what the object in question is. Also of interest, it's useful and interesting that this helps us understand a matrix by way of its columns. Columns of a matrix are fundamental to the matrix in various ways. And we're going to, again, see one of those in just a few minutes. More throughout the course. But so this is connecting the idea of a matrix being understood by its columns with the idea of how to do algebra with it. So this is conceptually useful. And in my experience, this one's just, from a conceptual level, just much more useful than the dot product formula. Okay. All right. Again, question of curiosity. How many people saw this in Math 218? Okay, good. All right. Okay. Linearity. Now, again, I know you've seen this before in Math 218 or 221, by the way, if anyone took 221. So linearity says this condition here is satisfied for any pair of vectors and any pair of real number coefficients. This equation here is satisfied. Different ways you can think about it. There's these different equivalent formulations. The way I like to think about this, just conceptually, is that if you do a linear combination before you plug into this function in question, versus if you do the linear combination after you plug in to the function in question, you get the same result either way. So linearity means that you can do the linear combination either before or after. Does that make sense, everybody? Okay, so I think this is a useful point of view. A lot to say about linear functions, of course. By the way, notice that I've restricted my attention here to functions that are what I like to call Euclidean functions, because they go from Euclidean space to Euclidean space. It's all we're going to talk about in this class. Now, you'll recall from 218 that there are more vector spaces than just Euclidean space, right? You can talk about all sorts of abstract, weird vector spaces full of functions, or vector spaces full of lots of different, full of matrices, lots of different things, right? But in this class, we're going to focus almost exclusively on Euclidean functions. Okay, how are we doing? Everybody remember this? Make sure that you're really comfortable, really fluent with the idea of what it means for a function to be linear. By the way, the term is linear transformation, and so you can call such a function a linear transformation. Very often, though, transformation's got a lot of syllables. It's kind of a mouthful. Very often, people will just say T is linear, and then it's understood that means it's a linear transformation. Okay. All right. Okay, so a couple of examples. This first one is a little bit weird. I'm going to phrase this colloquially as dot products are linear. Now, that is understood in an appropriate way. The function in question, when we say dot products are linear, what I mean is that I'm going to take some fixed vector and talk about dot products with that vector. That is a fixed given, not going to change. That's just that's part of the definition of what the function is what that left vector A is. So given that vector A, I can talk about what happens if I dot with that vector. And that's a function that takes an input x and gives you an output p of x. Everybody happy? Okay. My claim is that this function is linear. So that's something that you can check. Now, again, this is a linear algebra thing, and I don't want to spend too much time on reviewing details of linear algebra. I just want to hit some highlights. Make sure you're comfortable with how you would go about demonstrating that this is, in fact, a linear function. Just real quick, I'll just say the main thing you're going to be doing is basically recycling, making use of known facts, known algebraic identities, algebraic properties of the dot product. And this kind of falls out as an immediate result. Okay. Alrighty. Similarly, the cross product is linear. Again, by which I mean I'm going to define a function by saying I'm going to do dot products with some fixed pre-designated vector A being given cross products with that given A. That's a function. It's a function again in the sense that if I give you some vector x to go into this function, then I get a resulting value c of x out from that function. And again, claim that function is linear. Again, to be proved by using established algebraic properties of the cross product. How y'all doing on that? All good? Okay. Alrighty. This next one's a weird one, and I think this is a really important fact of linear algebra. Maybe will get mentioned in 218, maybe not. I hope so. But 218 is another one of these classes where they've got a lot of material to cover. They have to make some tough choices. They can't tell you everything about all of linear algebra. Tough choices are made, so you may or may not have seen this before. But there's another statement about linearity. This time, it's about determinant. This function I'm going to define here is about determinant. But I want to be very, very careful as to what the function is. The function is not determinant by itself. Determinant does not act on a vector. Determinant acts on a matrix. That's not what we're doing here. Determinant as a function on matrices is not linear. It's easy to generate examples showing that. What we are defining here as our D function is, I'm going to kind of indicate it like this. That's our D. This function, where not just one vector, but actually several vectors are given and fixed and not allowed to change. That's just set as to what those vectors are. If I then think, all right, if I were to take whatever input vector I'm given and use that as the bottom row in a matrix whose other rows are all those given vectors, and if I take the determinant, this function is linear. So there's different ways to say this. I mean, as I've stated this property here, we could say that, let me say this. The casual terminology, the colloquial usage here is to say that determinant is linear in its bottom row. And so the in its bottom row is a way of saying I'm thinking of it as a function only of the vector in the bottom row, and then everything else above is fixed. Okay, another way to say this, I'm getting ahead of myself. I've stated this property here for the bottom row. There is an analogous version of this for every other row. It's a little bit harder to highlight with the stylus. It's also there is an analogous version of this in every column. And all of these statements together, that in every row and in every column, determinant is linear in all those rows, it's linear in all those columns, all together that is known as multilinearity of determinant. So in general, multilinearity of determinant is a pretty big deal in linear algebra. It's very useful in a lot of ways, and a good thing to know. And ultimately, it's a statement about linearity, suitably interpreted. All right, now again, I'm going to pause for questions. Anybody? Everybody's happy? Okay. By the way, just maybe another thing I'll throw some words at. Questions are good, and I encourage questions. I hope you'll ask questions. I do have a discussion on the Sakai site about asking questions and trying to point out the different ways in which asking questions in class can be a good thing, usually is a good thing. There are, of course, some kinds of questions that are better left for office hours. You don't have to worry too much. I mean, yeah, try to make the obvious choices there, but if you're on the fence and not sure, should I ask this question or should I not, go ahead. And if it's more appropriate for office hours, I'll just say so, and it's no problem. But anyway, I encourage questions, and you're very welcome, and I hope you'll ask questions. Okay. All right. Okay. All right. It kind of looks like an elephant. Okay. Okay, here's another really important fact of linear algebra. How are we doing on time, by the way? Let's see. I have until 11:05. Okay, we're doing great. Another really important fact about linearity. If you have a Euclidean linear transformation, then it can be represented with a matrix. And vice versa. If you have a function that can be represented with a matrix, like so, that is a Euclidean linear transformation. Right, so this is an if and only if. These are equivalent formulations. Loosely speaking, I'll say linear transformations can be represented with matrices. And again, that's loosely speaking. We do have to restrict this to the Euclidean category. I have to be clear about what I mean by represented by a matrix. But linear transformations, think matrix. Right? Now, this part of the proof, that every matrix thought of as a function is a linear transformation, is straight computation. That's an easy one. That's a good practice problem if you want to make sure that you're good on what linear transformations are. Make sure that you can prove that this function is indeed a linear transformation. Okay. Where it gets interesting is going the other way. So simply from knowing this non-constructive statement about, the function that I'm visualizing has a certain property, right? That doesn't tell me what the function is, right? This is a non-constructive thing. Just knowing information, descriptive information about T, being able to conclude that it is in fact represented by a matrix. And furthermore, I'm going to be able to find that matrix. This is a harder problem. And I think it's really important for everybody to know how this part of the proof works. It's ultimately not that big a deal. It's just a clever observation. So keep in mind that when you have a vector, that vector is a linear combination of the standard basis vectors. Oh, that's by the way, a point that a lot of students are maybe a little loose on. So E1 means a 1 in the first position, followed by all zeros after that. And the subscript tells you where that 1 is. So E2, along those same lines. Oh, come on, stylus. What's going on with my stylus? Oh, I'm having technical difficulties here. There we go. E2 has the 1 in the second position. So again, subscript telling you where the 1 goes. So reminder, these are called standard basis vectors. Presumably you've seen these in Math 218. Very important, we're going to be using standard basis vectors a lot. Sometimes they are written with a different, sometimes this is written as I, or sometimes I with a hat over it, and this is sometimes written as J, or with J with a hat over it. Either is fine. I like E1 through EN because it allows me to generalize, right? It's a lot easier to talk about E1 through EN than IJKLM, comma, dot, 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 and then what letter do you do you end with XYZ? Because those variables are probably used for something else. You get into a notational problem. Okay. All right. So let's see here. I need to erase all of this junk. So yeah, every vector is a linear combination of the standard basis vectors, where you use its coefficients. It uses its coordinates as the coefficients. So I hope everybody remembers that. It's another fundamental fact from linear algebra. So that being the case, notice I can crank out T of X. I can expand what's on the inside. I can invoke I can invoke linearity. Notice that all that's happened in this step here is I've used linearity. So the linear combination that was on the inside is now linear combination on the outside. Right? What does this buy me? Keep in mind what I'm trying to prove. All I know is I'm allowed to use linearity, as I just did, but I need to show that this thing, T of X, is a matrix product. So how am I going to get now, let's see here, I'd like to fit all of you. There we go. I would like to fit this formula for T of X. I would like to view that as being a matrix product. And how am I going to make this? How am I going to make this happen that I make this turn into that? And well, you look at what we've got. I have a linear combination of T of E1 through T of En. I need that to be a linear combination of A1 through AN. And so the obvious choice is to just define my columns, A1 through AN, to be T of E1 through T of En. You make that choice, and as desired, T of X is AX. Just like we want. How are we doing? Is everybody happy? Okay. It's a really clever proof, and I want to point out that this proof does two things. It doesn't just establish that what we claimed was true, it even goes better. It establishes that what we're saying is true, and it gives us a formula for how to compute the corresponding matrix. If you want to know the corresponding matrix, yeah, sure, cool. Just plug the standard basis vectors into your function. Boom, those are your columns. There's your matrix. So really cool argument, very important argument in linear algebra. Okay, is everybody happy with this argument? Okay. All right, one last thing I'm going to say about 1.6, and then we're going to declare victory on that, and this will finish us for the day. and again, you may have seen this, but you may not have, and I think this is an underappreciated point. Matrix multiplication, such as here where I multiply these two matrices, corresponds to compositions of linear transformations. Compositions being, when you plug the output from one function into as an input for the next function. And I say corresponds here in the sense that, if S is represented by A, and if T is represented by B, then converting the transformations, reconceiving of them as matrices, the composition in that translation ends up being a matrix a matrix product. So again, a really important fact, sometimes swept under the rug, but I want to make sure everybody's seen this. All right, and that does it for time. So I'm going to draw the line right there, and we finished 1.6. We're going to pick up with 1.1 on Friday. Good to meet y'all, and see you on Friday. Have a good day.